Welcome to G Fun Facts Online. Today we're diving deep into an unseen crisis, a silent threat unfolding in our planet's waters. It's called thermal stress, and it's driven by the relentless rise in water temperatures. This isn't just about a slightly warmer swim. It's a global phenomenon that is fundamentally reshaping life in our oceans, rivers, and lakes, from the sunlit shallow S to the dark, abyssal plains. It's pushing countless species to their absolute physiological limits and unraveling the intricate food webs that sustain them. The story of thermal stress is a complex one, woven from climate change, pollution, and our land use practices. Understanding it is a crucial step in safeguarding the future of our blue planet. So where is all this heat coming from? The primary driver is global climate change. Our planet's oceans have been heroic, absorbing about 90% of the excess heat generated by greenhouse gas emissions, acting as a massive buffer that has slowed down atmospheric warming. But this service comes at a tremendous cost. Since the 1970s, our oceans have been steadily warming, and the trend is accelerating. The last decade was the ocean's warmest since we started keeping records in the 1800s, and 2023 officially became the hottest year ever recorded for our seas. This warming isn't happening evenly. Some regions, like the Southern Ocean, are taking up a disproportionately large amount of heat, and it's not just a surface-level problem. The heat is penetrating deeper and deeper, with about a third of the excess heat being absorbed 700 meters below the surface. This deep ocean warming contributes to sea level rise through thermal expansion, and messes with the ocean currents that regulate our global weather patterns. While climate change is the global engine of this crisis, many local factors are throwing fuel on the fire, particularly in freshwater and coastal areas. This localized heating is often called thermal pollution. One of the biggest culprits is the use of water as a coolant in power generation and industrial processes. Power plants, both fossil fuel and nuclear, withdraw colossal amounts of water from rivers and lakes to cool their machinery. This water is then discharged back into the environment at a significantly higher temperature, creating thermal plumes that can cook the local aquatic habitat. Urbanization also plays a major role. Think about our cities. Vast expanses of paved surfaces like roads and parking lots absorb and retain immense heat from the sun. When it rains, this accumulated heat is transferred to the stormwater runoff, which then flows directly into streams, rivers, and lakes, raising their temperatures. One study found that urban streams were, on average, a shocking 3.8 degrees Celsius warmer than nearby forested streams. Finally, deforestation, especially the removal of vegetation along riverbanks, makes things worse. The canopy of trees acts as a natural umbrella, providing shade and regulating the amount of direct sunlight hitting the water. When we cut down these trees, we expose the water to more sun, leading to significant warming. So we have this combination of global and local factors creating a pervasive threat. But what does this actually do to the creatures living in the water? For the vast majority of aquatic species, which are ectotherms, their body temperature is directly controlled by their environment. For them, temperature is a master variable, dictating the very pace of life. As temperatures rise, their metabolic rates accelerate. This increased metabolism demands more oxygen to fuel their cells. But here's the cruel twist. Warmer water holds less dissolved oxygen. This creates a dangerous double squeeze, where the demand for oxygen skyrockets just as its availability plummets. This leads to intense physiological stress, reduced growth, and in severe cases, suffocation. Fish become weaker, their immune systems compromised, making them more susceptible to diseases and parasites. Reproduction is also thrown into chaos. Many fish rely on specific temperature cues to trigger spawning, ensuring their offspring hatch at the perfect time. Elevated temperatures disrupt these delicate hormonal cycles, causing mistimed spawning, reduced fertility, and lower survival rates for eggs and larvae. For example, even slight temperature increases can completely disrupt the reproductive endocrine activities of tropical fish. Invertebrates, from tiny zooplankton to mussels and clams, are also hit hard. Mussels and clams are particularly vulnerable. As adults, they are relatively immobile and can't just swim away to find cooler water. Thermal stress also interferes with the calcification process, making it harder for them to build their protective shells. Perhaps the most visually stunning and heartbreaking impact of rising water temperatures is coral bleaching. Corals have a vital symbiotic relationship with microscopic algae called zooxanthellae. These algae live inside the coral's tissues, providing up to 90% of their energy and giving them their vibrant colors. When water temperatures rise just 1 to 2 degrees Celsius above their normal summer maximum for a few weeks, the corals become stressed and expel these algae. What's left behind is the transparent coral tissue over the white skeleton, a ghostly phenomenon we call bleaching. A bleached coral isn't dead yet, but it is starving and highly vulnerable to disease. Even the coldest parts of our planet are not safe. Polar marine life in the Arctic and Antarctic is highly adapted to cold, stable temperatures. They have slow growth and long life cycles, which makes them incredibly sensitive to warming. The rapid loss of sea ice is eliminating critical habitat for animals like polar bears, seals, and walruses, who rely on it for hunting, resting, and breeding. The struggles of individual organisms inevitably ripple outwards, triggering a cascade of ecological consequences that can destabilize entire ecosystems. One of the most immediate responses is a massive shift in where species live. As their traditional habitats become too warm, marine and freshwater species are migrating towards the poles or into deeper, cooler waters. This redistribution of life is happening at an incredible rate. Marine species are migrating, on average, 72 kilometers per decade. That's 10 times faster than species on land. While this is a survival strategy for some, many species can't move. Those in high-altitude lakes or at the poles may find they have nowhere left to go, facing local extinction. These migrations are creating what scientists call novel ecosystems, where species that have never coexisted are suddenly forced to interact. This leads to new competition and predator-prey relationships, disrupting the established balance. For instance, as warmer water species move in, they can outcompete native cold water populations like trout and salmon, squeezing them out of their habitats. The very structure of aquatic food webs is also being degraded. Research shows that in warmer, nutrient-rich waters, food chains are becoming shorter, with a marked decline in top predators. This is a huge concern because top predators are crucial for maintaining the stability of an ecosystem. At the very base of the food web, phytoplankton, the microscopic plants that are the foundation of aquatic life, are also in trouble. Changes in phytoplankton communities have consequences for everything up the food chain, from tiny zooplankton to the largest whales. Rising temperatures also accelerate the rate of decomposition, which, when combined with nutrient pollution from sources like agricultural runoff, can fuel the growth of harmful algal blooms. These blooms can suck the oxygen out of the water, creating vast dead zones where most aquatic life cannot survive. This crisis isn't just happening in a vacuum. It has profound impacts on human societies and economies. Fisheries, which provide critical protein for billions and livelihoods for millions, are highly vulnerable. The poleward shift of fish stocks is creating chaos for fisheries management. Traditional fishing grounds are becoming less productive, and conflicts are arising over access to these shifting resources. Projections for the U.S. East Coast suggest a potential 20 to 30% decrease in fish harvests by 2060 due to warming waters. Then there are coral reefs, the rainforests of the sea. They support a quarter of all marine species, protect coastlines from storms, and are the cornerstone of tourism economies around the world. The widespread coral bleaching caused by thermal stress is leading to a devastating loss of these benefits. The economic impacts of reef degradation on fisheries alone are estimated in the billions of dollars globally. Degraded reefs also mean less tourism, with some estimates suggesting an 80 to 90% reduction in visitors, causing job losses and crippling local economies. Without the protective barrier of a healthy reef, coastal communities become more vulnerable to storms and sea level rise. The total economic cost of coral reef degradation is staggering, with some studies estimating losses in the tens of billions of dollars. So with this escalating crisis, is there any hope? Yes, but it requires a massive, multi-pronged approach. The single most critical solution is to turn down the heat at its source by drastically reducing greenhouse gas emissions. This means a global transition to renewable energy sources, as outlined in frameworks like the Paris Agreement. This is non-negotiable. At the same time, we need local adaptation strategies to build resilience. This includes managing thermal pollution by using cooling towers at power plants and implementing nature-based solutions in cities like green roofs and permeable pavements to cool stormwater. Restoring and protecting critical habitats is also key. Planting trees along riverbanks provides shade, and protecting mangroves and seagrass beds buffers our coastlines. Marine protected areas, or MPAs, can act as safe havens, reducing other stressors like overfishing and allowing marine life a chance to adapt. Scientists are also exploring innovative ideas like assisted evolution, which involves selectively breeding heat-tolerant corals to enhance the genetic resilience of vulnerable reefs. Ultimately, addressing thermal stress requires a collective effort, from international policymakers to local communities and individuals. By combining ambitious global action with targeted local strategies, we can work towards a future where our planet's vital aquatic ecosystems can not only survive, but thrive. The fate of our oceans, rivers, and lakes, and our own, truly hangs in the balance. Thanks for tuning in to G Fun Facts Online.